Now I'd like to welcome Dr. Ian MacRae. Uh, Dr. MacRae is a professor with the University of Minnesota's Department of Entomology. He's stationed at the Research and Outreach Center in Crookston, Minnesota, and he conducts research and extension programming on the management of insect pests of field crops. Ian was awarded his PhD from Oregon State University in 1994. He researched small grain and rangeland insects at Colorado State University from 1994 to 1997 and is now at the University of Minnesota. His research focuses on the spatial and temporal distribution of insect pests. In the past several years, he has been using remote sensors mounted on UAS or drones to determine the within-field distribution of insects and plant disease in various agricultural crops. So welcome, Dr. MacRae. I'll pass it over to you.
Thank you very much, Victor. Yes, as Victor had said, we have a number of individuals who are involved in this. It's a very, very large author section. But what you'll find when you do this kind of research is the teams that are involved in doing this research have a tendency to be very multidisciplinary, and they have a tendency to be very large. It fits well into my particular training in integrated pest management, which is the idea of treating insect pests only when necessary. And basically the rationale for doing this is to fit into more efficiency in agricultural production. Well, we're in a situation now where the population in the next 36 years or 34 years is supposed to exceed 9 billion. The problem is there's not a lot of extra arable land out there, so we're going to have to actually increase our yields through efficiencies. I love this picture. It's of the State Fair in Minnesota on Labor Day weekend, and I anticipate that's what downtown Minneapolis is going to look like by 2050. Precision agriculture is a relatively, it's not a new term. It's been around for a while, but we're starting to see a revisiting to it, and that's probably because the technology has caught up to a lot of the theory. As I had said, my training was in integrated pest management. It was the idea of treating when necessary. Precision ag takes that to the next step, and it's treating not only when, but where necessary. Unfortunately, this requires very detailed within-field maps of pest populations. Now, we did some work a number of years ago on site-specific management of aphids as they were colonizing seed potato fields, and they were vectoring virus diseases, which were very impacting. And what we found was, yeah, they colonized the edge of the field first. They stayed there for about 14 days before redistributing into the field. It provided the producer with a good opportunity for targeted application. And we found you could have the same level of control using about 17% of the insecticide compared to doing a whole field application. There's a number of companies and individuals who use this technique even now. The downside of that was mapping that one research field, which was a 40-acre field, took about 16 man-hours a week just for that one 40-acre field. Now, crop scouts are trying to hit upwards and beyond 15,000 acres a day. So obviously, this method of being on the ground and getting those detailed maps is just not adequate. We need a more rapid data acquisition method, and remote sensing using canopy reflectance could very well be that method. Now, remote sensing is something that human beings have done for a long time, all our lives, and probably the life of the species. If you think about it, you come home after being away for a few days, you open the fridge, there's a carton of milk in there, you take it out, and you're going to have a big glass, and you're going to just take a big slurp, and you think, wait a minute, I bought this several days before I went away. Is this stuff still good? Well, there's a couple of ways you can test it. You can pour a big glass and start drinking it down, or you can give it a smell. The smell is the remote sensing way, and it's the way that most people would go. And so we actually have been using remote sensing as a species for many, many years. And it's just the way of measuring something without directly contacting it, assessing it from a remote measurement. And in agriculture, this is something that we've been doing for many, many years, typically with satellites. We've been using it on the ground as well. But UAS, unmanned aerial systems, is just a relatively new technology, and the technological advancements in both the vehicles and the sensors really have been driving the adoption of this technology into agriculture. As you know, the light that's coming off the sun is quite varied. You have very, very short gamma rays all the way up to very, very long radio waves, and the visible spectra that we see is quite short. However, most of the spectra that we're interested in assessing plant health is either in the visible range or one of the visible range wavelengths or just beyond that and down into the infrared. And I'll talk a little bit more about that as we go on. The technology behind the vehicles themselves, well, we've used a number of different vehicles to remotely sense agricultural fields, like satellites. They undoubtedly take the largest footprint, and they're probably economically the best bet for your money as far as data acquisition is concerned. But the problem is, if they take a shot when it's cloudy, you do not get data, and you can't call NASA up and say, hey, can you send that bird back today? So you're stuck on their orbital satellite schedule. Airplanes we've used as well. Airplanes take a smaller footprint. They're much more immediate than a satellite is. However, very expensive. You have to hire a pilot. The equipment has a tendency to be very expensive as well. On the very other end of the spectrum, you have the person on the ground, that chap who's driving along on his four-wheeler, and he has a very small footprint of what he can see, but what he sees is very, very detailed. Using UAS as a platform for remote sensing is somewhere between that person being on the ground and being on an airplane. It's less expensive than an airplane. It's much more immediate than airplanes and satellites. However, it gives you much greater resolution than either of those, but not quite as good a resolution as being on the ground. If you want to put this into kind of visual means, this would be the level of satellite. That would be what typically you'd see from an airplane. This is kind of more upon the UAS level, and then when you get down to the ground, you can actually see the insects on the plant. Now, when we actually use remote sensing to look at insect populations and assess populations, we're not actually looking at the individual insects. What we're looking at is the impact the insects have on the reflectance that's coming off of the canopy. In other words, what effect they're having on the plant health. Now, the reason we can do this is because obviously not all wavelengths that are coming down from the incident light are going to be used by the plants. Green and yellow are obviously reflected. We see that every time we look at a leaf. The reds and the blues are actually used in photosynthesis, so they're absorbed by the plant. They're used by chlorophyll. But near IR is near infrared, which is just beyond the red, and it's beyond the range that we can see. Also is not absorbed by the plant. The photons don't have enough energy to run photosynthesis. So plants have evolved to reflect that light. And the way they reflect that light is well, the first thing that happens when you stress a plant is that you see a decrease in chlorophyll. Now, not only does that mean you see a decrease in the chlorophyll that's made, but you also see a decrease in the processes that are constructing chlorophyll. So you see a decrease in the overall chlorophyll. You also see a structural change on the cells within the plant leaf, especially palisade parenchymal cells and the spongy parenchymal cells. Now you have the chloroplasts where the chlorophyll is are starting to break up. That's one of the changes. But stress also induces these other changes in the cells. And the cells, especially the palisade parenchymal cells, are the cells that are responsible for reflecting a lot of that near infrared. And what that means is when you see the chlorophyll start to decrease and you see the cells that are responsible for reflecting the near infrared, you start seeing a difference in what's called the spectral signature. Now that's just the amount of light that's being reflected in all of the wavelengths of incident light that we're measuring. And this is a good spectral curve. This is done with a radiometer, which actually measures the amount of light that's being reflected across a number of different wavelengths. And in a healthy plant, you can see that nice green line that goes around. There's a dip down in the red, and that's because it's using that red light, it's absorbing the red light, and a very, very high response, a very high reflection of near infrared. It doesn't want to absorb that near infrared. Those parenchymal cells are still quite healthy, and they're reflecting the near infrared. If you look at the unhealthy plant, which is that orange line, you see you don't get nearly the dip in the red wavelengths, in that red block, so it's not absorbing as much red light. And also it doesn't reflect nearly as much near infrared. Now this means that when we have stressed and non-stressed plants very close together, we can tell them apart based on their spectral reflectance. And that now gives us a tool to start looking at levels of plant stress that may be associated with insects and disease. In our research, we use a number of different kinds of vehicles. We typically like to use the multi-rotor UAS. We like to use something that can hover because a lot of our work is plot work. We're looking at the impact of different levels of insects that we're manipulating in the plot. And so we really like the loiter time that we get over the plots with the rotor vehicles. If you're doing this from a more applied aspect, you're much more likely to use a fixed wing. It'll give you longer time in the air. It gives you it's a much more economic platform. It'll cover more land or cover more ground. Sensors that we use range anywhere from a purpose-built camera that sees the near-infrared and then probably red and green wavelengths like the ADC Tetracam, which is a brand name, right through to a modified camera. Now that Sony is a camera that we have had modified. Every digital camera is sensitive up into the near-infrared to about 1100 nanometers, which is beyond what you can see. You can see up to about 600 to 640 is where red ends. And so the camera that you have in your back pocket in your cell phone actually can see the near-infrared, but they filter it out so you don't get a fuzzy picture. Well, you can modify a camera so that it will allow near-infrared back to the digital sensor, to the CCD, and filter out perhaps blue instead. And so you change the filters inside the lens and inside the camera, and it allows you to start recording information that can start providing information on the healthy plants, the reflectance of healthy plants. There's also a number of purpose-built sensors. There's a number of companies out that are producing these. However, a lot of producers are actually flying visible cameras, or flying GoPros. And there's a lot of very good data and very useful data you can get from just a visible camera. And I'll talk about that in a few minutes too. The sensor that you select really does depend on the mission. If you're interested in looking at specific wavelengths and the effect of in particular insect and disease impacts on specific wavelengths and specific reflectance, you're probably going to use a radiometer, which is not an image device. It actually looks at mathematically the amount of light that's coming back. However, for management purposes, we're much more likely to use something like an image and produce things called false color near infrared. Now, the reason they're called false color near infrared is, well, have you ever wondered what a near infrared picture would look like to your naked eye? It would look like that. We can't see the infrared of the near infrared, so we wouldn't see any response. So when we actually look at a bright, vibrant near infrared picture with all the pinks and all the reds, we've actually assigned red to take the part of near IR or of infrared, and therefore we call them false color. I talked about visible data, and there's a lot of things you can do actually with visible data. Look at hail damage, look at planter skips, look at stand establishment. Pesticide or herbicide drift becomes especially clear using visible data, and also things like water management. Up here in northern Minnesota, we're extremely flat. We have a lot of overland flooding, and so a lot of our producers who are either thinking about using this are actually looking at the possibility of gee, can I fly this thing in the spring and take a look at what my fields look like and decide whether or not I've actually ditched them correctly. And basically, any problem you can see from the ground, you can see more clearly from the air. There's a number of software tools that we use in this process as well, because when you think about it, the airplane is flying over, the vehicle is flying over a field, and it's taking shots as it goes. Those shots have to be stitched together, much like making a jigsaw puzzle, and there's a number of different software that we use. We've used Agisoft and Pix4D and a number of other ones, but it basically takes those images and starts to put them together into one large image. Now, this is a potato field, research field that we fly and do some work on in defoliation, and that's not just one image. That's actually a composite of about 128 images. And up in the upper right, you can see two yellow dots, and that's actually the same individual. The airplane caught him twice. He had just moved on to the next plot when he was counting. So this stitching is, and putting these things together into one large, takes a variety of different kinds of software. When you have your image in one piece, you can start to use a number of other pieces of software to analyze it. There are a number of different ways of analyzing these and looking at the reflectance. NDVI is probably the most common, normalized difference vegetative index, and that basically looks at the ratio of the near infrared and the red that's coming off of a canopy. It's a way to measure plant health. It's also a way to kind of get some indication of what your biomass is as well. There are many other indices that you can use, vegetative indices. This is just probably the most well known. But it allows you to start, these wavelengths that you're detecting allow you to start managing these and manipulating these different vegetative indices and getting different data about the status of your crop canopy. Now, we've used these techniques in a number of different systems, and the first one, probably our largest project, is looking at soybean aphid. Soybean aphid is an invasive species. It's the most important insect pest of soybeans in the northern U.S. And what we have found is even NDVI provides us with a very good indication of what kind of plant or what kind of populations may be out there. In other words, NDVI does actually change depending on the number of aphids that are out there. So stress of those aphid populations and the time that they're out there feeding actually will cause a change in NDVI. And in fact, we just published that paper in Journal of Economic Entomology. We're also now working on which wavelengths are being affected by soybean aphid and trying to differentiate them from some of the diseases that we get in soybeans. We've looked at other insects like sugar beet root maggot. This is an interesting insect to work with because it's subterranean. It's actually feeding on the roots of sugar beet. And so it's very difficult to scout because it's underground. So it's all destructive sampling. You have to pull the beetroot up and start looking. And so this project allowed us to evaluate remote sensing as a way of trying to assess insect populations using just the reflectance. And we were very happy with our results. You can see these are false color near IR images. The top comes from a plot that has very low sugar beet root maggot populations, and you can see very vibrant reflection of the near infrared, very, very bright. The picture on the bottom is from a high sugar beet root maggot population and not nearly as much near infrared being reflected. So yes, there was a huge impact of the population of root maggots on the reflectance. The interesting thing about that data is I not only did it with photographs from a small UAS, but I also did ground measurements with a radiometer. And when I did the ANOVA on the NDVI values from the imagery, I found there was a significant difference, and that was great. That means we're seeing an impact. But when I actually started charting out the spectral curves from the radiometer, I really didn't see that much of a difference. You have the spectral curves. The red is the high populations, the yellow is the medium, and the blue is the low, and they just sit right on top of each other, and there's no significant difference between them until I started breaking out the data by variety. That was just pooling all of the data. But there were 3 different varieties in that trial. And what I found was I had one variety that really didn't have much of a spectral response between high and low sugar beets. I had one that had a moderate response across from low to high sugar beets. And I had one that had a significant response between high and either low or medium levels of sugar beet root maggot feeding. And unfortunately, what that means is there are huge varietal differences, potential varietal differences in reflection. And the influence on the spectral curve may just, or there will be varietal influences on these differences in spectral reflection. And that's going to complicate differentiating the images and the damage, and it is something that we're going to have to work on. Another estimate, or another way we've been working on is using this technique is looking at defoliation. Now this seemed to us to be relatively low-hanging fruit simply because when an insect is actually defoliating your plant and eating the plant material, it's fairly easy to tell because it's gone. So we had a project where we were looking at defoliation by Colorado potato beetle, and if you've ever worked with Colorado potato beetle, you'll know they're an incredibly effective defoliator. They can take a plant right down to a stub. And in this project, we would go out weekly, and we would have a crew that would go through all of our plots, and it was that picture of that field you saw earlier. And they would calibrate their eyes and calibrate what their defoliation estimates were at the beginning of each day, and then they'd go through, count beetles on random plants in the plot, and then estimate the defoliation, and then they'd go through the entire field. At the same time, we were actually flying the fields, and we were taking imagery that we could then use to estimate defoliation from the images. The software that comes along with many of the cameras and that's available for image analysis, many of them, well, almost all of them, will allow you to actually train the software to identify things. Now this, of course, is near-infrared data. Potato canopies are not pink. And in this case, the green is actually the bare soil. And what we did in this case is we actually trained the software to recognize and differentiate between plant material and soil. Then we delineated the center 2 rows of the plots, which is where we were taking our estimates from, and they were our experimental rows of the plots. And then we just told it to estimate how much of the area inside that blocked area was defoliated, and then we could start calibrating that or correlating that with a number of beetles. And what we found when we statistically compared them, we ran a regression on it, and what we found was that in the near IR and in the visible data that we were getting, both were very, very closely associated with the visual estimates that we were getting on the ground, which is the way you do it if you were actually managing that field. And so our results indicated that the defoliation estimates from our aerial images were at least as accurate as estimates from ground observers. And that paper is actually in preparation right now. We have a number of other ongoing projects that we're doing in the lab. We're looking at damage from a number of different insect feeding types. We look at wild rice borer. Wild rice is a crop in Minnesota, and wild rice borer is an important insect. As I've mentioned, we're looking at sugar beet root maggot. We're looking at soybean aphid and Colorado potato beetle. And that project actually allows us to compare a stem borer, which is responsible for lodging, a subterranean feeder, a phloem feeder, and also a defoliator. So we're able to look at these different types of insect feeding and try and differentiate and come up with patterns for them. We're also working with a number of diseases. We have collaborative projects with people working at potato virus Y, which is a virus important in the seed potato industry that's vectored by aphids. I've also got a collaborative project with our wheat pathologist here at the research station looking at bacterial leaf streak. And one of the most important ones we're working on right now is differentiating between stressors. Now, we can't do this very well right at the moment. We can see stress on these spectral responses, but it's very difficult to tell the difference between what is actually causing that stress. So right now we're looking, unless of course it's defoliation, but right now we're working on being able to tell the difference between, say, soybean aphid and brown stem rot or sudden death syndrome in soybean. And I would imagine that eventually where we're going to go with this technology is we probably won't get to the point where we'll say, here's the reflection, it's right at 970, and that's soybean aphid. And the reason I feel that is because of this confounding issue with varieties and with other stressors. But I suspect where we're going is symptomological models. So it'll be this time of year, it'll be these environmental conditions, you'll have this reflection, and it'll be a 95% chance that that problem is soybean aphid and a 60% chance that it's brown stem rot or white mold. And so I feel that's where this technology probably will go first. As for the diseases, the work on PVY, that picture's on the left-hand side of the screen. You can see the top is a healthy plant. It's not infected with PVY, very vibrant, very bright reflection of the near IR. That plant down below is PVY infected, much duller. These are taken actually, these are actually clips from the same photograph. So the picture beside that is the bacterial weed streak project. That field is basically visible, completely green, but you can see in the center those little hotspots, those yellow hotspots. Those are actually areas where we inoculated with weed streak, bacterial weed streak, and it's about 4 days post-inoculation, and we're starting to see those. The symptoms are not yet visible to the eye, but certainly we can see them with near infrared. So there's a wide variety of applications for this technology. It has an incredible amount of promise, and as FAA regulations change and we see more and more greater adoption, we start working out these problems, you're going to see a lot more of this technology in agriculture, and like I had said, it has incredible promise at the moment. Do I have time for a few questions, Victor, or other questions? Is Victor there?
Yes, if anybody has any questions, feel free to put them in the chat box. And you can have Ian respond to them at this moment. Prices on the sensors.
That's a good question. Very good question, Dennis.
They vary quite a bit, but
yeah, they sure do. You know, we're starting to see sensors out there that have say one visible camera, and then maybe up to 3 specific wavelengths in the near IR, and that will give you certainly enough data to do a number of vegetative indices. And I've seen those priced anywhere from about 3,000 to 3,500 up to about 6,000 and 8,000, some of them. And so it all depends on if you're looking at these kind of sensors. I'd look at I'd look at product support. I'd look at what the software suite was like, get a feeling for how easy it is, and also get a feeling for what the software suite actually will allow you to do. And also how easy it is to export the data, which is another big one. Is some of these cameras work very well. The data works very, very well within its own software systems, but maybe not so well with the others. The other thing you have to be cautious about is looking at how the data is compressed in that digital camera. If you're looking at a converted camera like that Sony or a Nikon or a Canon, oftentimes they start compressing the bits, and uncompressing them can sometimes be it's not impossible, but it is another hoop that you would have to jump through. And so you want to make sure that the product that you get and the software suite you get are going to be, give you exactly what you need. Michael, UAV coverage per flight and battery life. On the multi-rotors, now Wayne's going to cover fixed wing quite a lot, but on the multi-rotors, the vast majority of them are anywhere between, say, 20 and 30 minutes max, and 30 minutes would be a much larger battery life than what we're flying. The smaller ones, we fly everything from a 3DR Iris, which is a quadcopter, and it's quite small, and that's specifically designed to carry something the size of a GoPro, although some of these sensors that we were just talking about are that small, and some even smaller than a GoPro. That usually has a flight life of 20 minutes, 25 minutes, depending on the payload. The one thing you want to make sure of is there's two kinds of UAS out there, one that's crashed already and one that's going to. And so you want to make sure that you're not kind of pushing that flight envelope too much, because your sensors cost money, your vehicles cost money, and so obviously. We actually have a large DJI S1000, which has quite a heavy payload, about 12 pounds. And that's a very large unit, and that thing will stay up easily for about 25 minutes. Some of the other ones will stay up for 30, and I've actually heard of one or two that'll stay up for 30 to 40, but I've not flown those. Any other questions?
If there's any other questions, feel free to put them in the chat box. I think we'll continue now. And start with our next presentation.
Oh, we had one more, drone deploy.
Oh. Yes. Are you familiar with Drone Deploy, which is a cloud-based image analysis?
We don't do it ourselves simply because we are doing our analysis in-house. We're looking, at this point, we're actually examining specific wavelengths, and so we're actually doing our own recording, and then we're downloading and working in the lab. I do know that Drone Deploy is one of the technologies that is very likely to be adopted into production. And when you talk to producers and you talk to growers themselves who are thinking about this idea of using cloud-based data management is very appealing to them, because it means they don't have to do it themselves, and it seems to be easy. There's a lot of the data that we get seems to be quite large, though, so it seems to be that may be one of the limitations. And Laurie, are you happy with the cameras that post-market sensors? Laurie, to be quite honest, the cameras with wideband filters, the reason that we're using them is because it's very likely what we may see from the production end of things. That's very likely what guys are going to be going with, is something on the less expensive end, and that's why we've incorporated them into our program, more from the extension area. But for the research area, yes, we do use more expensive sensors with narrow band filters. It gives us a much better result. We usually have our narrow band filters for very specific wavelengths, and usually not the ones you buy that are going to be available off the shelf, because a lot of those seem to be specifically for nitrogen, and we're looking at slightly different wavelengths. So, but there are a couple of companies that we do work with, and that we have ordered sensors from, and that we've used, and yeah. So for the research purposes, I would say sensors with much more narrow bands, and probably from an extension viewpoint and just looking at broad NDVI, looking more at the wideband filters and the modified cameras, because we feel that's what may end up in in the marketplace.
Great. Excellent questions. Thank you, Ian. All right, so our next presenter is Dr. Wayne Wolt. Dr. Wolt works at the University of Nebraska-Lincoln and is the project leader for the E-Extension UAS and Agriculture Learning Network, and has developed a research and extension program on the application of UAS in agriculture and natural resources at the University of Nebraska at Lincoln. Specific areas of research and education include UAS deployment and flight operations, performance characterization of autonomous navigation systems, sensor system development, sensor integration, and information management. He has a private pilot certificate and has been conducting flight operations for 3 years within the context of FAA